Slide visible now?
Yes.
Okay. So the last class we discussed about overfitting, and now today we'll start so more machine learning approaches under supervised setting. And today we start with support vector machine. It is a very popular uh, kind of classifier, and in general it is being used for this data which are linearly separable. So linearly separable data means then we can get some sort of linear hyperplanes or linear, maybe if it is a two-dimensional data points, then we can have a line. If there is a multi-dimensional data point, maybe if it's a three-dimensional, it is a two-dimensional plane, but it's a linear plane. And if it is a multi-dimensional, that is a multi-dimensional hyperplane. Generally, one dimension less than the dimension of the data points. Okay, so but there is a question: the data which has been given, are these data are always linearly separable? So that is a very interesting kind of question, that what we'll see in these particular mm, lectures of support vector machine. Okay, but first we start with our concept. Since we are familiar with logistic regression kind of problem, then we start understanding the support vector machine thing from a logistic regression viewpoint. And then we try to formalize more mathematically and try to understand these issues, that if data points are not given in a linearly separable form, then what should we do? Okay, and then we see that how SVM is going to help in these scenarios. Okay, so let us start the data in this SVM. So first of all, what is the optimization objective here? So now we are starting for, then in case of our logistic regression thing, that we are trying to classify between two set of data. Okay, let's see, this is the one set of data, this is another set of data, and we are trying to find out some this decision boundary, I think this thing. And what is our, that in linear regression our data function is theta transpose x, but in case of our logistic regression we put a nonlinearity over this, so that become our is theta x, that is the hypothesis function, and this g theta is generally called sigmoidal nonlinearity. And it has been that what is the sigmoidal, that we know that g z is equal to 1 by 1 plus e to the power minus z. Okay, so that is the basic understanding. well minus z. As z is here, z is now theta theta transpose x. Just put it here. E to the power minus s minus the transpose x. And if you recall, what is the basic understanding of sigmoidal? This is 0.5, this is 0, and this is basically 1. This is 1. You can understand that if theta transpose x is greater than 0, greater than is equal to 0, then this e to the power this g of theta. So actually, if this, then h theta x basically is very much close to 1. So as you see that it, if it is greater than 0 in this thing, it is slowly going to the 1. And if theta transpose x is less than 0, so in this part it is converging, this is theta x is converging to the 0. That you see, that is converging to the 0 and is converging to the 1. Okay, so this is the sigmoidal nonlinearity. Okay, so what we actually want, that if y is equal to 1, so what is that? If y is equal to 1, that means the actual ground truth is 1, the class belonging is actually 1, that our hypothesis, that estimated hypothesis is also very close to 1. Then we can get a right estimation. And so that what does this mean? That means theta transpose x is greater than. Okay, so this is we want, is exactly what we are trying to do, because to achieve this we have to find this. Okay, so it is our way that we have model, we have trained our model in such a way that if y is equal to, if we want to y is equal to 1, let's put tx greater than is much more than g. Okay, so then you can get this. So that is very clear to you actually. Okay, now, and if y is equal to 0, that means class belongingness is 0, then we, what we need is theta x is very close to 0. Every is close to what should we require is theta x is less than 0 say both should. That is, it is very clear to understand. So that much I just recall for your recapitulation, that we already know in case of logistic regression. So if you have any question, you can ask that. You just forget it anything. Now we have represent this logistic regression from a different viewpoint. Now you see what is the cost. As you see, that is this cost function is basically a find of maximum maximum likelihood estimation viewpoint. We basically use this cost function. Cost function was, the y, this is common minus, so y of log of h theta x and 1 minus y log of 1 minus h theta x. Actually this is minus, this was minus log and this is minus log, so that is just we take the minus common. So here you can see that now your h theta x is what? H theta x is equal to, is basically 1 by 1 plus e to the power minus transpose x. That you know, that is our the sigmoidal hypothesis function. Now we just put it here, that minus y, so I just minus is come to y log of 1 by e to the power minus transpose x. Now this is again minus because this minus is there. 1 minus 1 log minus 1 minus log of 1 minus 1 by 1 plus theta transpose. So we we just replace h theta x as this. Okay, so this is the thing. Now, if you try to plot it, so this is log 1 by x. This is basically 1 by x, and x is 1 plus e to the power the transpose x. So now if we plot it, now here you can see why that also we have discussed earlier, why this is the cost function. Now you see, if y is equal to 1, what we want? We want the transpose t is greater than 0, because if theta transpose t, as we see earlier in slide, is greater than is equal to 0, that denotes that h theta x is going to 1. Okay, as per our this this kind of thing, that is the thing. If it is going to greater than is equal to 0, so either jayega, so it is going to 1. It is converts to the 1. Okay, so here also same thing we are showing. If it is a this thing, that it is. So you see here, if this is equal to 1, if we get this function, so this function you see, if it is we going to this is basically a z means this. Now if it is going here in this going to 1, so our error error function is basically coming to the 0. So that means if we get that y is, if y is equal to 1, so theta transpose x, if z is equal to theta transpose, if theta transpose x is going to 1, so you can see h theta is also going to greater than 1. So that is that this converging is. Now that is the, what is the idea is that if it is so, our loss is very, you can say, less, if we can achieve this. So loss is very, is close to 0. So loss is also close to 0, because this is the right prediction. But if, even if y is equal to 1, and if we go, if we go in a different side, we can have a greater loss. So it's an infinite loss kind of thing. So that's why we can get this time we can have very high loss. If this is going to, if y is equal to 1, so y is equal to 1, and z is basically going to the in minus side, so we can incur a very high loss. If we go to the z is equal to go to the 1, then greater than 1, so it is basically a very low loss kind of thing. So this is the idea. Okay, now what we can say, we can approximate it. Now this is 1, this is value is 1. Now here put, you can say this is a kind of a curve. Now if this curve is approximated with those two straight lines, this is 1 more than 1, it is greater than 1, and is less than 1. Now if it is less than 1, then what is the cost are increasing. Is greater than 1, it is cost is decreasing. So we are approximating in this way. A similar thing here for this particular case. Y is equal, y, if y is equal to 0, what happened? This is the same thing. If the y is equal to 0, what we required, we want theta transpose t is greater than is equal to 0. So now if it is going to less than 0, then you can say the cost is being very less. So this is the cost curve, this is the curve of the cost function. So it is become very close to 0. But if it is a greater than 0, if y is equal to 0 is greater than 0, so base cost is very infinitely high. Same the same thing, that also we can is minus 1, so we can approximate in this way. You can see that this particular curve is approximated by another two straight line. Okay, so these things also we can say that this cost function may be approximated by this particular. geometrically. Okay, so any question you can ask. Now this thing, this approximated curve, we call this approximated curve is cost 1. So because it is a cost 1, we just name it the cost 1 of z, and it is a cost 0 because it is y is equal to 0, this is y is equal to 1, that's why cost 1 z, and cost this is called cost 0. So this cost function, we are going to make it more simply because this is a kind of logarithmic curve, but we can make it more simple and more, you can say, easy to handle mathematically because these are only two straight line. Okay, so it's the approximation. Now you see. Now from the logistic regression, what is this? That was this minus log of h theta xy. So this particular thing, if we use this particular approximation, this part become cos theta 1 theta transpose xi, because we can do that. And this part, when y is equal to 0, this part become cost 0 theta transpose xi. These are the approximation we have made. We just write it in this way. And we can put a regularization. This is a regularization term. As you know, this is the regularization term as we see in the last class. Okay. Now, if we say, now, if we called, if we approximate it, okay, then we called it support vector machine. I'll come why we call support vector machine. But just this is the approximation of this particular idea. Okay. Now what we just make the same thing, mean, because this is our cost function, so we have to minimize this on with respect to theta. So 1 by m is our normalization factor. This is 1 is equal to 1 to m. I is equal to, this should be I is equal to 1 to m, because this is now I is equal to total number of you can say data samples yi. So this part is approximate cost I theta transpose x and xi plus 1 minus yi cos theta cos 0 theta transpose xi plus this is the regularization. Okay. So this is the n number of thetas are regularized. So if we see in this point that you can see that these functions, this is your cost support vector machine cost function. This cost function is equal to something that this, if it is a lambda, so a, this total thing is a plus lambda into this total thing is b. So this in this format we can say. So this total thing, this total minimization, whatever, this total thing is called a, and this part, this is lambda. Lambda छोड़ के जो बाकी part है, this we can say the b. So we can say that this, we can say CA into B, where if I just lambda say dono say B, if you just divide, then CA plus B, so C is equal to 1 by lambda. In that sense, we can write in this way, we can write the same this function, that mean theta into C. 1 by m is now it becomes C. So 1 to m is equal to 1 to m. This value, this particular value, yi cos I theta transpose plus 1 minus this plus 1 by theta squared theta j squared. Then this m or m cancelled because this m and this m has cancelled actually. Okay. Okay. So what is the SVM hypothesis then? This SVM hypothesis basically mean of theta. So we have to minimize this function with respect to theta, and y is equal to 1 to m. M is a number of, m is the training sample. Yeah. Training samples. Okay. So, and y is equal to this cos I theta transpose x and 1 minus y. Cos 0 is 1. So that, as we just mentioned, and half this is the normalization. Now, what is the hypothesis? S theta is equal to 1 if theta transpose x greater than or equal to 0. And if it is 0, this is otherwise. So, this is the basic hypothesis. And this is the hypothesis function, this is the cost function. So, this is the SVM what we have. Now, what does this mean? This means that this transfer, this support vector means machine, we can see as a large margin classifier. Why large margin? Because you see that this is a kind of cost curve is something like that previously, and it is in this case this is a kind of logarithmic curve. Now what we'll see that we can approximate such a way that that time theta transpose is not theta transpose tx is greater than 0, greater than equal to 0. Now I say no, we can put not 0 is not thing. We can put greater than equal to 1. You can see it here. So this is theta transpose 0. And this kind of theta transpose tx is less than is equal to 0. But we can put it, no, it is a, it should be 0. So it should be minus 1. So this is exactly in this. So that idea is basically that if y is equal to, we have some sort of approximated such a way that this z greater than is equal to 1. So we have to look if we say in this way, if you see in that case that y say large margin, if this is the something and this is some data. Now initially we have a this kind of. Now what we are saying, we have put a margin of that. Okay, this is a two guidelines kind of thing we put here. Because of this, because this guideline, it is initially greater than equal to, now it's greater than equal to 1. So if this is a decision boundary, we have two guidelines. This is a 0 and this is 1, this is minus 1. Very hypothetically for your just I write it for your simple understand. Okay, so there is a two guideline you can put it here between these two data points. So that's why the margin. So initially that is a single line. Now we can say we can guard it. Some guideline we put. Okay, so there is a, and there is a kind of, we say that if this width is high, that is much more robust classifier. Okay, that is very easy to understand. So this is exactly what we can show here. That if it's equal to 1, we want theta transpose is 1, not just this. We can put a some sort of buffer space in both directions. Okay, that's why it is called the large margin. We will show some of the other you can say um, representation of the similar thing. Okay, if you have any question you can ask. So here you can see that the same SVM decision boundary. I will say that now this is our basically the SVM hypothesis function. Hypothesis function is basically a decision boundary. That is the DB. Okay. So this is yi cos I theta transpose xi plus that is whatever. So now y is equal to 1. So then theta transpose xi, initially it is what? Xi greater than is equal to 0. But this thing is basically for this line. Now we have put a guard line here. What is the guard line? Guard line is this. There is it. And this is another guard line here. That guard line is basically here. Okay, because this is a, if it is a plus case, this is a minus case. Okay, now exactly it is been shown here. So this is basically the actual your logarithmic curve, and we have approximated using some sort of buffer. Okay? So exactly this is happening. If you have any question, you can ask. This is a very good concept. If you understand this question properly, and that when we go for a some more advanced mathematical model, you could understand very easily. So as you know from the logistic regression view things, we put that how actually what is the basic understanding of that. So one understanding is very very crucial here that I'm trying to say here. So that this is that what we already seen, that this is a just for thing. This is kind of, and we can put a guard point, and we have some fat margin classifier, or is it some large margin classifier. And now the question is, if we even if I defined it, how we are going to define this? Okay, so that is the basic thing, how we are going to define this margin. So this is an open question. Now we will come. Let's see. Now you can see that if this particular thing is 0, as c is a very big, if you put it as a big number, it's, let's say it is 10 to the power 10. So it's a very very big number. So it's a minimization function. So you have to minimize this. If it is a very high, then this function becomes 0 because it's a very big number. So now the thing that whenever y is equal to 1, this is we have to 0, and we have to mean this particular thing. I the mean of I think this total function will boil down 1 by f. This is only when this is y is equal to 1. Let's be very clear about it. Okay, and when this is y is equal to 0, this transpose is again minus 1. So then if this is basically that the basic thing is this, then theta xi is equal to greater than is equal to 1 if xi is equal to 1 and less than is equal to 1, y is equal to 1. Okay, so this in this way you can also the decision boundary kind of thing. Now this you can see there is a the linearly separate. What do you mean by linear separability? Now one thing we first understood that this linear separable curve, that there is a two set of data points here. So linearly separable case means there is a some sort of linear line, plane, hyperplane, whatever is exist between two data sets. Okay, so since if these data points are such that we can have such linear linear decision boundary, and decision boundary may be straight line. This is a 3D case, and if it's a multi, it's a linear. If it's a multi-dimensional case, okay. But how you know So how you know which particular this separator is good? Okay. You can say you can say no sir, I choose this. Another your friend say no sir, this will be better. You can say that. So what we are trying to say, that we are trying to find out such a separator we can get the highest breadth. So highest breadth means this. Okay. You see that this highest width kind of thing. And if you say that this particular line touch upon few data samples, for let's say this is positive side, this is negative side, so some data sample in positive side, and this particular line is touch upon some data sample in negative. So you can say that somehow data sample, negative data sample, and these two positive data sample is somewhat useful to define this. Okay, so there is some sort of some points. These points, which points are basically helping to find out if bad margin, the high margin classifier. It's called these data points actually, and these data points are called support vectors. So these data points are called support vectors. These data points are this is the closest data point of this line, the line, and the closest data point, or they touch the data point almost. So these data points are going to tell you that in which guideline is maximum. This maximum guideline you can get for this particular data set. And these data points is called support vectors. Okay. And since these support vectors are associated of this defining this fact margin classifier, so this called support vector machine. In short, SVM. Okay. So how the support vector is coming. So, but this linearity property is very important here. If you have any question, you can ask. This is a very simplistic and very geometrical description of support vector machine.
So what if the examples could not be separated? Let's say there is an X where an O is and an O where the X is. Then what would happen?
Yeah, you were saying this. That is, you are saying this. Okay. That there is no linear straight line exist of this data point. That is your question?
Yes, sir.
Yes. That's a very good question. That is I'm coming. So as of now, this is our definitely it is not a linear case. Now it is a very interesting example. I do not know because it is the problem of online class, but still I'll try. Let I say our two hands. Okay, two hands we can just try to draw here. So this is our hand. So this is I write it uh, to just for our hypothetical. Please think about our hand. It should not be look like this. Let this. This is the situation. These are our fingers. It definitely not look like our hand, but for understanding I'm saying. Now, if you say we can easily, you can say another hand. Here the this our fingers are like this. We can easily do that because this kind of we can put our fingers in between. Now you see our tip of the fingers, okay, are your data points. Okay, these are the data points. So my question is that if we say this tip of the fingers are data points, is this a linearly separable or not? Because you see there is no linear line, so you have to, if you have to separate it out, you have to light it like it there. Okay, so there is clearly linearly non-separable. Okay, fine. Now if I say that your one hand is here and there is a, you just make it a, there is a kind of depth here and your this hand is something like here. So actually what I'm trying to say, your one hand is here and other hand is here. So there is a some sort of depth if it is at this point and this point. So we just making it. So if you do this, now these points are now even linearly separable. What I'm trying to say, actually, now the data points, initially data points are this. This is one hand, and this is another hand, fingertips. So definitely, if you say in that sense, that is basically not separable kind of thing. This kind of thing is initially situation is something like that. Now, if there is a, in the two different planes, let's see, this is the one fingertip and another is the another fingertip, but this there is a distance, so there is a plane and this is a plane actually. Now it is a two different plane, you can say, because you just take the concept. So even if it is in a in a one two dimensional, this is not separable, linearly separable. If you go in a third three dimension, so you can, that means what? If you just open up this hand, so then what happened? Then there is a, this is a linear plane separating data points. What are data points? The fingertips data points. So what is the point? That this very easy example, as a very practical example, you see that these data points are not separable in two-dimensional plane, is two-dimensional plane, but it is linearly separable in 3D plane. Getting my point? If you are not getting to, I'll repeat it because it's a very interesting. Now the question is that it may be the case that the point clouds or whatever the point clouds may be non-separable in a particular dimension, but if we transform it, if we project in a higher dimension, you may have a linear hyperplane in this higher dimension, on those higher dimensions, to separating out the data points. Okay, and that is one of the major goal of what we'll see in the later class, that how we'll get into that we'll see the kernel trick kind of thing, that how SVM kernel is going to help it. So we can find this nonlinear transform from one dimension to higher dimension. You got your answer?
Yes, sir. Thank you.
Okay, so this is a very interesting and it's a good question. Okay, so this is the idea, and it is called margin. That's what I said. This particular thing is called the margin. Okay. Now the question is that there is a sometimes there is a problem in this is an outliers. Okay, kind of sensitive to. So C is very large. Even if you can see that this is your particular thing, and this is your other kind of thing. So you could see that this is maybe a right decision boundary. But sometimes if you go that you know this is a kind of this point is outliers, but still it's possible to get find something that this is also concept that we have because we have just discussed in the last class, that this kind of outliers, should we consider this kind of outliers? Because this particular decision boundary, we can say, definitely lose some of some generality, because if we say that this particular this is a distribution, okay, and sorry, this is one distribution and this is other distribution, then definitely this point is something is not very close proximity of this distribution. So it may be a noise or outlier. Okay. So, but should we consider this outlier? That is very important. So C is very large. So kind of this kind of this C means here the C. What is one by this C actually? Here we can see in last slide. So I'm not going there, but this is called. So that is important to understand. So this concept, this thing is always there. Okay. Okay. So in this particular thing, in this particular class, today's class, we what if we summarize it, that what we going to understand, that we have a basic problem of uh, these two things. Just a second. Okay. So these two things we have basically touched upon, that that may be the problem is this. So we can get a classifier or decision boundary here. So the idea is basically this. So which decision boundary get? So what we said, based on this, based on this point, we can find a guideline. That guideline you can, this is a kind of margin we can get based on this, the closest data points with respect to this decision boundary, and then we can get, we have to try to maximize these guidelines, and the point which is basically playing a crucial role to find out these guidelines called support vectors. Okay, it's called support vectors, and these support vectors will go to find help to understand, I will give you and that particular, that which particular you can say decision boundary we are going to choose. And then we start with a very important question, that maybe there is some points that maybe it is not linearly separable. So this is kind of this, but in some higher dimension, maybe some uh, in higher dimension, that this there is some sort of hyperplane in between these two, that we have to see. So with this I conclude today's class.